Hello, sir.
Hello, how are you?
I'm fine, sir. How are
Okay,
you?
I'm good. So, in the last class, we finished the chapter atom. So, today we'll discuss the chapter nuclei. Okay, so in this chapter, we will have first topic nucleus structure. Okay, nucleus structure. So, earlier we know that atom is there. This is atom. Hmm? This is atom, and at the center there is positively charged nucleus, and electron revolves around the nucleus. Now, entire mass and positive charge of an atom, because we know that atom have the negative charge also because of the electron, and positive charge because of the nucleus, because nucleus is positively charged. So entire mass or whole mass and positive charge of an atom is concentrated into a very small volume called nucleus. Okay, so this nucleus is very very small, smaller in size as compared to the size of the atom. If you want to see, you can see here. If you take one atom and you will calculate the radius of that atom, you will get 10 to the power minus 10 meter. 10 to the power minus 10 meter. And radius of the nucleus, you will get something around 10 to the power minus 14 to 10 to the power minus 15. Means you can say that the atom is 10 to the power 5 times larger in size as compared to nucleus. So I am just showing you the comparison. This is my room and this is the tip of the pen. Okay, I am sitting in a room and this room is uh, quite bigger as compared to this pen. So the see the tip of the pen. If you will compare, if you are comparing the size of the nucleus and the atom, so this room will be the atom and this tip of the pen will be the nucleus. So you can see how small the nucleus is as compared to atom. After that, nuclear structure. Inside the nucleus, there are neutrons. Inside the nucleus, there are neutrons and protons. And these neutrons and protons inside the nucleus are known as nucleons. So nucleus is made up of neutrons and protons. Nucleus is made up of neutrons and protons. These neutrons and proton is known as are known as nucleons. Now, proton. What is proton? So proton is basically hydrogen nucleus. You can say proton. You can say a hydrogen nucleus. Okay. Why hydrogen nucleus? Because in the hydrogen nucleus there is only one proton. Because atomic number of the hydrogen is one. So in the nucleus of hydrogen, remember, there will be only one proton. So sometimes we represent proton with hydrogen nucleus. Okay. So what is the charge on proton? Proton is positively charged, we know. So charge on proton is equal to the charge on electron. And electron is negatively charged. So charge on the proton is 1.6 into 10 to the power minus 19 coulomb. Mass of the proton, just a minute. Uh, Nawal and Nafisa, is my voice okay?
Yes, sir. Yes, sir.
Okay, so mass of the proton is this 1.6726 into 10 to the power minus 27 kg. 1.6726 into 10 to the power minus 27 kg. And this is equal to 1 AMU. AMU is basically the atomic mass unit. Okay, and this is also represented by 1 mu. So basically, if someone is asking what is the mass of proton in AMU, AMU is a unit of mass. Okay, AMU is a unit of mass. Like kilogram is a unit of mass now. So this AMU is very small unit. Okay. So if someone is asking what is the mass of the proton, you will say 1 AMU, or either you will say 1.67 into 10 to the power minus 27 kg. And AMU is represented by mu also. Now, what is the symbol for the proton? Proton is represented by this symbol of hydrogen. So this is the hydrogen is written as 1 and 1. Mass of hydrogen is 1. Charge on hydrogen is also because in hydrogen, basically, this I will explain you later. Okay, what is this? Here you should understand this. The symbol of the proton is this, and this is represented by 1 and 1. The meaning of this you will get to know. Neutron. Now neutron. What is neutron? Charge on neutron is 0. Mass of neutron is this 1.67 in 1.6749 into 10 to the power minus 27. So this is also approximately equal to 1 AMU. Okay, this is also approximately equal to 1 AMU, and symbol is N, 0 and 1. So now you can see, you can compare the mass of the proton with mass of the neutron. So see, mass of the proton is 1.6749. 1.6749. So mass of uh, uh, proton is this 1.6726, and mass of neutron is 1.6749. Means mass of neutron is slightly more than the mass of proton, and approximately we assume the mass of the proton and the neutron as 1 AMU. Okay, approximately. After this, what is atomic number, mass number, and atomic mass? Atomic number, mass number, and atomic mass. So basically, what is the atomic number? There are elements in the periodic table: hydrogen, helium, lithium, beryllium, magnesium, chlorine, oxygen. Okay, we have elements. So for those elements, there are different atomic number. Now, what is the atomic number of an element? The number of protons in the nucleus will be the atomic number. The atomic number is basically the number of protons present in the nucleus. For example, helium has two atomic number. So in the nucleus of helium, there will be two protons. Now, what is mass number? This is mass number. So mass number is basically uh, number of protons plus number of neutrons in an atom or inside the nucleus, you can say. Or we know that the protons and neutrons are the nucleons. So you can say either you can say number of protons plus number of neutrons, or you can say number of nucleons also. And mass number is represented by A. This is mass number, and this now we will discuss atomic mass. I told you that earlier, the whole mass of the atom we consider the mass of the nucleus. So basically, atomic mass, we will take the mass of the nucleus. Okay. So atomic mass will be the mass of nucleus. Okay. And what is inside the nucleus? Inside the nucleus, there are protons and neutrons. So mass of nucleus will be mass of proton plus mass of neutron. Okay. So mass of proton plus mass of neutron can be calculated like this. Inside the nucleus, number of protons plus number of neutrons, number of protons plus number of neutrons inside the nucleus. And mass of one proton and mass of one neutron is 1 AMU. So you will multiply number of protons plus neutrons with 1 AMU. And number of protons plus number of neutrons. You can see number of protons plus number of neutrons is atomic mass or mass number. So basically, atomic mass can be written as mass number multiplied by AMU. Okay, or you can write it as 1 AMU. And 1 AMU is equal to 1.6 into 10 to the power minus 27 kg. You have to remember atomic mass, mass of nucleons. Atomic mass is nothing but mass of nucleons. And what are nucleons? Number of protons and neutrons, or you can say number of protons and neutrons inside the nucleus are the nucleons. For example, this is some element X. Okay, this is some element X, and now I will tell you what is the meaning of these symbols. This X and this is Z and this is A. So basically, this Z will represent the. In this case, this is the element, and this is Z and this is A. This Z will represent the atomic number. Atomic number of the element. And atomic number is equal to the number of protons. Okay, no problem. And what is A? Mass number. A is the mass number. So for this element X, atomic number is atomic number is Z, and mass number is A. So that's how an element is represented. For example, this is the oxygen. Okay, and 8. What is 8? 8 is the. Okay, I am removing this. 8 is the atomic number, and 16 is the mass number. Okay, if I say that calculate the number of protons and neutrons in this, and one more thing, in some books you will get this can be written like this, or in this way also you will get the oxygen is this atomic number and mass number can be written. Okay, so we will calculate here total number of protons in this oxygen atom and total number of neutrons, total number of protons and total number of neutrons. So total number of proton is what? Atomic number is 8. So here in this oxygen atom 8 protons will be there, and number, if you want to calculate the number of neutrons, so number of neutrons, from here you can calculate. Okay, mass number is equal to number of protons plus number of neutrons. So what you will do here, mass number A is equal to number of proton plus number of neutron. So mass number is what? This is mass number A, and this is atomic number Z. Okay. So what is the value of A? Put the value of A as 16. Number of proton is 8 because 8 is the atomic number, and plus number of neutrons. So number of neutron you will get 16 minus 8 means 8. So in this oxygen atom there are 8 protons and 8 neutrons. 16 minus 8. If you want to find the neutrons, number of neutrons, then simply subtract 8 from the 16. Subtract A minus Z. Okay, you will get number of neutrons. So here you can write number of neutrons is given by A minus Z. A is the mass number, Z is the atomic number. Now for this chlorine atom, this is the chlorine atom. This 6 is the atomic number, 13 is the mass number. So in this chlorine atom there will be 6 protons, and how many neutrons will be there? 13 minus 6, 7. 7 neutrons. Okay, so in this way you have to calculate. Now this topic is very easy. Classification of nuclei. Classification of nuclei. So basically in some cases what happened, element. Some element founded in nature in different forms. Okay. And one thing here I want to tell you, element will be decided by the atomic number. Element will be decided by the atomic number. Okay. If atomic number will be same, then element will remain same. Okay. So here is isotopes. So what are isotopes? Isotopes are the atoms of same element. Means, what is the meaning of atoms of same element? Suppose hydrogen element is there. So in nature, hydrogen have different forms also. Okay. With the example, you will understand. Atoms of same element whose nuclei have same number of protons but different number of neutrons. So basically, in case of the isotopes, Z or atomic number will remain same because number of protons remaining same. Okay, this is same, and mass number will be different. Okay, because there are different nucleons. Okay, so this will be different. Now with this example, it will be clear. Suppose hydrogen hydrogen element is there. So in nature, hydrogen is found in three forms. Okay, 1H1, 1H2, 1H3. Now you can see here, in this hydrogen element, these are the three forms of hydrogen atom. Of same atom, okay, of same element, there are different atoms. These are different atoms of same hydrogen element. Now you can see, here is one, here is one, here is one. Means this is the atomic number, this is the atomic number, this is the atomic number. Atomic number is same. Atomic number is same, mass number is different. So these are what? Isotopes. They can ask you the definition in 1 mark. What are isotopes? So you will say atoms of same element whose nuclei have same number of proton but different number of nucleons. Or you can say in this form also, atoms of same element having same atomic number but different mass number. I think this will be easy. Atoms of same element having same atomic number but different mass number. Don't get confused here. Remember example, okay? With the example, it will be clear. After that, this is one more example here. Now this what is the element name? Chlorine. So this is the chlorine atom. This is another chlorine atom. This is one chlorine atom. This is another chlorine atom. And these two atoms of chlorine are different. How? You can see atomic number is same. Atomic number is same, but you can see the mass number 35, 37 mass number is different. So atomic number same, mass number different means these are isotopes. After that, this topic is related with the isotope. Fractional atomic mass. Okay. For example, this chlorine have two forms. One chlorine atom is in this form, another chlorine atom in this form. These two forms you will find in nature. Okay, but these two forms have different composition. And if we want to write the average mass, then how we will write the average mass of the chlorine? Because in the books you will see the chlorine is written like this, 1735.5. Sometimes we write chlorine like this, and 35.5 is basically the average mass. Is basically the average mass of the chlorine, and this average mass is due to the different isotopes of chlorine. There are two isotopes of chlorine. Okay, so you will understand. If you want to calculate the average atomic mass, and this formula is this A1, N1, A2, N2, A3, N3. What is A1? Atomic mass of first isotope, atomic mass of second isotope. N1 is the fraction of first isotope, N2 fraction of second isotope. This will be clear with this example. For example, this is the chlorine atom, and this chlorine atom have this mass. This is not given. Okay, this is not given. So basically, chlorine atom is founded in this two forms. We find chlorine in nature. Chlorine atom, there are two different chlorine atoms. Okay, of same element, there are two different atoms founded in nature having different composition. For example, this type of chlorine atom is 75%, and this type of chlorine atom you will find in nature 25%. Okay, this having the atomic number 17, but mass number different, 35 and 37. So what was the formula to, if you want to find the average mass of the chlorine, average mass, because now you can see one atom of chlorine having a mass of 35, one atom of chlorine has a mass of 37. So which mass you will take? You have to take the average mass now. And for calculating that average mass, we will use this formula A1, N1, A2, N2, A3, N3. And what is A1? A1 is the atomic mass of, first you can take first this or you can take first this. Okay, so this is 35 multiplied by the fraction of composition, so it will be 75%. So 75 divided by 100 plus 37 multiplied by the composition, fraction of composition, 25 by 100. So when you will calculate this, you will get 105 plus 37 divided by 4, and finally you will get the average atomic mass of the chlorine as 35.5 AMU. So that is why we write chlorine as mass of chlorine as 35.5 because of the isotope. So next topic is isobars. Isobars. In case of the isobars, mass number remains same, but atomic number is different. For example, this is the example of isobars. This is the carbon atom, this is nitrogen atom. So you can see mass number is same, but atomic number is different. You can see argon, okay, and this is calcium. So you can see mass number same, atomic number different. So these are isobars. Isobars. After that isotones. So isotones, atoms of different element whose nucleus have same number of neutrons but different number of protons. So basically, in case of the isotone, atomic number will be different. Okay. Okay. Atomic number will be different. Mass number will be different. But A minus Z means number of neutrons will be same. Number of neutrons. You can see here. Lithium and beryllium. These are two atoms. Now, what is the atomic number of lithium? 3. What is the atomic number of beryllium? 4. So atomic number is different. Now come to the mass number. 7, 8. Mass number is also different. Now calculate number of neutrons. How to calculate the number of neutrons? Mass number minus atomic number. 7 minus 3. 4 neutrons. 8 minus 4. 4 neutrons. So number of neutrons are same. So these are isotones. So these are isotones. So isotopes having same atomic number but different mass number. Example is this. This is also the example of isotopes. And after that fractional mass, after that isobars, after that isotones. Now what is the shape, size and the density of the nucleus? Shape, size and the density of the nucleus. So basically we assume nucleus as spherical in shape. But nucleus is not a perfect sphere. So there are some variation in the shape. So basically, the deviation will be either less than or equal to 10%. So basically, it is not a perfect sphere. But for all practical purposes, shape of the nucleus is considered as spherical. So we will consider the nucleus as sphere. Okay. So basically, nucleus is founded by the Rutherford, and he did the experiment and find that the volume of the nucleus is directly proportional to the number of nucleons in the nucleus. More number of nucleons means number of protons plus neutrons inside the nucleus. More number of nucleons, more will be the volume of nucleus. This is founded out by experiment. So if suppose V is the volume of the nucleus, A is the uh, number of nucleons means mass number also. So you can write V as the volume, number of nucleons as A. So V is directly proportional to A and A is the mass number. Now if this is the nucleus and we are considering nucleus as a sphere in shape, then volume of the sphere can be written as 4 by 3 pi r cube. So I can write this volume as 4 by 3 pi r cube. Okay. So this is the volume of the nucleus, this is the mass number. So volume of the nucleus is depending upon the number of nucleons means mass number. So this is 4 upon 3 pi r cube. Okay, so this expression can be written as r cube is directly proportional to 3a divided by 4 pi. And this mass number for a particular nucleus will be same. 4 pi is also same or constant. So you can say r cube is directly proportional to A. Okay. And when you will remove this proportionality sign, before that, R can be written as A to the power 1 by 3. You will take cube root on both sides, you will get this. So when you will remove this proportionality sign, you will get a new constant, that is R naught. Okay. And R is the radius of nucleus. And this R naught is the radius of nucleus. Not R naught. R is the radius of nucleus, and R naught is a constant. This R naught is constant. And the value of this constant, and this is constant for all nuclei. Constant for all nuclei. If you will take the nucleus of hydrogen, if you will take the nucleus of chlorine, so that this value will remain same. Constant for all nuclei. And the value of this R naught is equal to 1.2 into 10 to the power minus 15 meter. And 10 to the power minus 15 meter is 1 Fermi. So R naught you can say is 1.2 Fermi. So basically this is representing the size of the nucleus. So if you want to calculate the radius of the radius means size. If you want to calculate the radius of different nucleus, you will put the values of different mass number. You will get the radius of different nuclei. After that, density of the nucleus. Density means mass divided by volume. Means in how much space the mass is distributed. Amount of mass is in a particular space is basically density. So now density of the nucleus is also known as the nuclear density, and this is represented by rho. And we know that if we are calculating the density of the nucleus, so density of the nucleus or density of any other thing also is given by mass divided by volume. So we are calculating for nucleus. So density of nucleus is mass of nucleus, volume of nucleus. Okay, so mass of nucleus is A into 1 AMU. Mass of nucleus is what? Mass of nucleus is mass of number of nucleons present in the nucleus. And number of nucleons is A. And for each nucleon, the mass is 1 AMU. So that is why A into 1 AMU will be the mass of the nucleus. And volume of the nucleus, we know 4.3 pi r cube. Now R is this. R is this. So from here, we can put the value of R here and we will get this. Okay. Okay. After that, this is the, I am solving one step here. This is A into 1 AMU. This is divided by 4 upon 3 pi. Now you can see the cube of this whole. So it will become R naught cube multiplied by, this is A to the power 1 by 3 and to the power 3. It will be A. So that is why this A and A is gone. Cancel out. Okay, so now you have 1 AMU and in denominator you have 4 upon 3 pi R naught. Put the values. 1 AMU is this 4 upon 3 pi and R naught value is this 1.2 10 to the power 150. Put the value. So after calculating, you will get density of nucleus is this, is very large density. The density of nucleus is very large. 2 into 10 to the power 17 kg per meter cube. If you will compare this density with density of water, see density of water is 10 to the power 3 kg per meter cube. And density of nucleus is this. And for different nucleus, this density will be different, slightly different. Okay. So density of the for different nucleus, the density will slightly change. So you can write one statement here. If someone is saying for all the nucleus the density is same, okay, so that this statement is not true. For different nucleus, the density will vary slightly. So nuclear density nuclear density vary with type of nucleus slightly. And the reason is isotopes, because for isotopes you will put here, when you will take into the consideration the isotope, this A and A will not be cancelled out. This A will be something different. Okay, so after this there is very easy question. This is the question from NCERT. So they are saying find the nuclear density for iron. Find the nuclear density for iron given mass of the iron nucleus or iron nuclei is equal to 55.85 mu, means AMU. Okay, this is the question from the NCERT. And mass number of the iron is 56. So we have to find the density. Now, what is the formula of the density? We are calculating the density of iron. So we will put mass of the iron multiplied by density of iron. Okay. Actually, we are calculating the density for the iron nucleus. Iron nucleus. Find the nuclear density for iron. So we will put mass of the nucleus divided by the volume of the nucleus. Mass of nucleus divided by the volume of nucleus. So mass of the iron nucleus is given 55.5, 55.85, and mu means AMU. And this is divided by volume of the nucleus. Okay, so we considered what? Nucleus as spherical in shape. R is the radius of the iron nucleus. So you can write 4/3 volume of the nucleus, 4/3 pi R cube. So from here you will get 55.85. This is AMU, and this is divided by 4/3 pi. What is the formula for R? R is equal to R naught A to the power 1/3. So we have a value of A, so we can write R naught multiplied by A to the power 1/3. Put all the values, you will get the answer. It will be 55.5, 55.85, 55.85, and 1 AMU is 1.67 into 10 to the power minus 1 AMU is equal to 1.67 into 10 to the power minus 27 kg. So put this value here. (1.67 into 10 to the power minus 27 kg). And this is 4/3. Pi you can take 3.14. R naught value is also, we already know, R naught is given by 1.2 into 10 to the power minus 15. And A is given in the question, 56. So this will be 56 to the power 1/3. No. One thing we have to change. Okay, just wait for 1 minute. So I have done one mistake here. So this is r cube. This is r to the power 3. And what is r? R is r naught to the power 1 by 3. So if you will do cube of this, so it will become cube of this, and cube of this will be r naught cube into a. So it will become r naught cube into a. Now put the values. 55.85 and 1 AMU is 1.27 into 10, 1.67. Yeah. 1.67 into 10 to the power minus 27, 4 upon 3, put the value of pi 3.14, and r naught cube means 1.2 into 10 to the power minus 15 cube and multiplied by a, given in the equation 56. So after calculating, approximately the answer will be 2.2 multiplied by 10 to the power 70 kg divided by meter cube. We do not have time. Okay, otherwise I will calculate this. Now, this is very interesting thing that we are going to study. Okay, before that, earlier, before 1905, we know that means the idea about the mass. So, mass is the amount of matter or amount of quantity present in an object, basically. But in 1905, Albert Einstein gave a new idea about the mass. Okay, and I think both of you already know a very famous equation, E is equal to mc square. That is very famous. So today we will discuss that. What is the use of this equation? This is world's most famous equation, E is equal to mc square. So in 1905, Albert Einstein, in his special theory of relativity, basically Albert Einstein gave his theory of relativity. Okay, Einstein gave two theories of relativity. One is general theory of relativity, another was special theory of relativity. So in his special theory of relativity, Einstein suggested that, or you can say said that mass is the form of energy. This is very strange thing. Mass is the form of energy. He predicted mass and energy are equivalent. What is the meaning of the equivalent? Equivalent means we can get idea from here. Means mass can be converted into energy, or energy can be converted into mass, or you can say it is better to say uh, if you are giving energy to this mass, what is the meaning of mass energy equivalence? if you are giving energy to this mass, na, this is the mass. So if you are giving energy to this mass, so the mass of this object will increase. Or if somehow this mass disappears, okay, in a nuclear reaction, you will see there will be a mass defect. Today we will discuss that also. If mass suddenly disappeared, not suddenly, somehow mass disappeared. So uh, if the mass disappears, so due to disappearance of that mass, there will be the equivalent amount of energy release. Basically, this is the significance of this. So you can see here, if energy of a body is increased by amount E, its mass is increased by m, and that mass is given by E by c square. Basically, this equation now, E is equal to mc square was in this form in his research paper. M is equal to E by c square. Means if you are giving energy to something, some mass, if you are giving energy to some object, the mass of that object will increase. This is very strange thing. Now we have one question. There, which has more mass, a stationary ball or an identical moving ball? Hmm? Nafisa, can you tell me which has more mass? Nawal?
Sir, the stationary ball.
Okay. And Nawal? Okay. So what I told you, more energy means more mass. So this stationary ball, okay, this stationary ball will have, okay, I can explain in this way. Uh, which has more mass? Okay. So we can explain this in this way. So if the ball is moving, suppose this is a ball and this ball is moving. So if this ball is moving, so this ball will have the kinetic energy. And I am not considering the heat energy. Okay. So basically, if this ball is moving, this ball will have the kinetic energy. And here is a ball that is at rest. And if it is at, and now you consider m is the mass of the ball at rest. There is a mass of the ball at rest. So mass at rest. Okay, this is the mass of the ball at rest, and this ball is moving, so this will have a mass at rest plus mass due to this kinetic energy. So mass of the moving ball mass of the moving ball is basically the rest mass at rest, because this mass, this ball will have this mass, and there will be one extra mass. There will be one extra mass. And what will be that extra mass? That extra mass is due to the kinetic energy. Is due to the kinetic energy divided by c square. You can see here. Mass increase means if you are giving E energy, then M mass will increase by this E by C square. So this wall is having the kinetic energy. So due to the kinetic energy, the mass, there will be one extra mass. So basically the moving wall will have the more mass. Okay, one more question. This is also very easy question. Find the increase in mass of 1 kg of water. 1 kg of water when it absorbs 4.2 into 10 to the power 3 joules of energy. So basically, suppose this is a glass, and in this glass 1 kg water is there. Try to focus what I am saying, try to understand. 1 kg water is there. Now you have given energy of 4.2 into 10 to the power 3 joule. This much of energy you have given, and according to the Einstein, if you are giving energy to any mass or to matter, the mass of that matter or mass of that matter will increase, and increase in that mass is given by energy given divided by c square, and now c is the speed of the light. So energy given is this 4.2 into 10 to the 3, 4.2 into 10 to the power 3, and c square means 3 into 10 to the power 8 square. So basically, approximately, you will get 4.7 into 10 to the power minus 40. For saving time, I already solved this. 10 to the power minus 14 kg. See, this small, this mass is almost negligible. That is why in practical life and in real life, when we are giving energy, so mass increases, but that mass is negligible, not significant. So that is why we are not observing that the mass is increasing. So you can conclude here, M mass is very small. But not zero. Okay. Now this equation E is equal to mc square. What is the meaning of this equation? So E is equal to mc square. If M mass disappears, then E energy will release. I told you. If M mass will disappear, then E energy will release. C is the speed of light in vacuum. C is equal to 3 into 10 to the power 8 meter per second. After that, mass defect and binding energy. This is very interesting topic. Mass defect and binding energy. So first we will discuss mass defect, then we will discuss the binding energy. Okay. So now see what is mass defect. Suppose these are the nucleons. These are the nucleons, and from these nucleons, this nucleus is made up of this. Okay, this nucleus, because these nucleons, okay, these are the nucleons, and by the combination of these nucleons, the nucleus will form finally. Okay. So formation of nucleus. Formation of nucleus. Okay. So basically, due to these nucleons, by the combination of these nucleons, the nucleus is formed. Now, if I am saying that mm, this is a person here, okay, and I am having two balls, three balls. I am having one ball, two ball, and three ball. So this is 2 kg, this is 1 kg, and this is 3 kg. And now I am giving these ball to this person. Okay, I am giving these ball to this person. So initially the total mass of three balls is 3 plus 1 plus 2, 6 kg. 6 kg na? So when suppose you gave these ball to this person, you have given. Now what will be the mass of these three balls? Nafisa? What will be the mass of these three balls? I am saying these three balls you have given to this person. Now you are asking what is the mass of these three balls?
6 kilograms.
Obviously it will be 6. But here this is not the case. These nucleons are combining to form a nucleus, but the mass of the nucleons, the mass of these nucleons is greater than mass of nucleus. It is founded that mass of nucleons is greater than mass of nucleus. So now why this is happening? And this is known as the mass defect. During the formation of the nucleus, some of the mass is disappears, and that is known as the mass defect. Some mass disappears during the formation of nucleus. That mass that disappears is known as the mass defect. Now expression for the mass defect. Suppose this is some element X, and this element X have the atomic number Z and mass number A. So in this element, number of proton will be Z and number of neutrons will be A minus Z. I told you. So if you want to calculate the mass defect will be the mass of nucleons minus mass of nucleus. So mass of nucleons minus mass of nucleus. Now what are nucleons? Nucleons means number of protons and neutrons inside the nucleus. So mass of nucleus can be written as mass of proton plus mass of neutrons inside the nucleus minus mass of nucleus. Now mass of proton, okay, number of proton in a nucleus is Z, okay, number of protons in a nucleus is Z, and when you will multiply that Z with mass of the protons, total number of protons, basically of proton, this mass of proton is basically mass of one proton we have taken here. And if you will multiply Z, means Z is total number of protons. So basically this will be the mass of all the protons. This will be the mass of all the protons. So represent this with capital M. So this will be the mass of proton. Mass of total number of proton. These are mass of total number of neutrons. So total number of proton is Z, and MP is the mass of one proton. And total number of neutron is A minus Z, and this is mass of one neutron. So basically this is mass of all the protons. This is mass of all the neutrons, and means this is the mass of nucleons. And M I am considering as the mass of the nucleus of X. So this will be the expression. of the mass defect. This is the expression for the mass defect. Now, due to, I told you that if some mass will disappear, means energy will release. And due to this mass effect, the energy release is basically the winding energy. So next topic is the winding energy. So basically what happens, these are the nucleons, and during the formation, this is the formation of nucleus. When nucleus forms, there will be the mass defect, and due to the mass defect, this energy will be released, and this energy is known as the winding energy. And this winding energy is delta E is due to the mass defect, so it can be given by delta M into C square, and delta M is this, so put this value here, and this is C square. So basically we define my winding energy like this. See this process in reverse. Means what is happening, you are giving delta E energy to break the nucleus, so that it will become like this. You are giving binding energy to break the nucleus or to separate the nucleons. You can say that is binding energy. So we define binding energy in this way. It is the amount of energy released to separate all nucleons from the nucleus. And binding energy from the nucleus, nucleons in the nucleus. So these nucleons are bounded due to the binding energy. Understanding or not, Hafiza?
Yes, sir.
This is very easy topic. Okay, so one question we will solve, and after that we will wind up. Okay, so in this question they are asking find the binding energy associated with mass defect of 1 AMU, and the value of 1 AMU is given. So this question is very easy, we can solve it. Mass defect is given. Mass defect means delta M is given. So delta M is given as 1 AMU. And binding energy is the energy due to the mass effect. So binding energy will be the delta E, you can say. You can represent binding energy with delta E, and delta E will be delta M into C square. So what is the value of delta M? 1 AMU. So 1 AMU into C square. C square means 3 into 10 to the power 8 meter per second square. And 1 AMU is given as 1.6 into 10 to the power minus 27 kg. So 1.67 into 10 to the power minus 27 kg. Okay, and this is 3 into 10 to the power 8 and square of it. Now we will convert this value into electron volt. In 1 joule, there are 1.6 into 10 to the power minus 10 to the power 19 electron volt. 19 electron volt. Okay, in 1 joule there are 1.6 to 10 to the power 19 electron volt. In one electron volt there are 10 to the power minus 19 joule. So 90 electron volt. You can check this value. Okay, I am not sure about this, so we will put this value here. 1.6 into 10 to the power Oh, actually this is mega electron volt. Okay, sorry, it will be electron volt. So it will be 1.6 into 10 to the power 19. Okay, and to convert this whole equation becomes in electron volt. To convert the electron volt into mega electron volt, you will multiply it with 10 to the power minus 6. In 1 mega electron volt, there will be 10 to the power 6 electron volt. So after calculating this, the mass defect you will get 931.5 mega electron volt. Okay, a minute. Actually, it will be in 1 joule. There will be 6.4 into 10 to the power 18. 6.242 into 10 to the power 18 electron volt. Okay. This was skipped from my mind. So this will be 6.242 into 10 to the power 18 electron volt. And to convert that electron volt into mega electron volt, you will multiply it with 10 to the power minus 6, and this value will be 931.5. And you can convert in this form also, means in 1 electron volt, there are 1.6 into 10 to the power minus 19 joule. So when you will convert now 1 joule, so it will be 1 upon 1.6 into 10 to the power 19. So basically it will be approximately equal to 6.242 into 10 to the power 18. Okay. Now from here, if there is a mass defect of 1 AMU, then the energy released will be 931.5 mega electron volt. If 2 AMU mass will disappear, then 2 into 931.5 electron volt energy will release. So we can convert our formula delta E can be written as delta M multiplied by 931.5 and mega electron volt, and this mass should be in AMU. Okay. Are you getting it? Means if 1 AMU mass will disappear, then energy will release. If 2 AMU mass will disappear, so 2 into this amount of energy will release. So we can convert this formula. Okay. Delta M into 931.5 mega electron volt, and this mass should be in AMU. Okay, the last topic. Nuclear stability and the binding energy. So in this we will discuss the stability of different nucleus, different nuclei. Okay, so this is one data. First we will read that data. The binding energy of heavy hydrogen. Heavy hydrogen is this: mass atomic number 1, mass number 2. In this, it is there is 1 proton and 1 neutron. So the binding energy of heavy hydrogen is this 1.1 mega electron volt. Binding energy. Binding energy means the energy which is required to bound the nucleons inside the nucleus. That is the binding energy. So for hydrogen, for heavy hydrogen, it is 1.1, and for uranium 238, uranium 238, this is 1800 mega electron volt. So if the atomic number will increase, if the mass number will increase, na, then binding energy will increase. You can see this hydrogen is having a mass number 2, so binding energy is this. This uranium is having a mass number this, and this have this much of energy. So binding energy increases with increase in mass number. This means uh, iron 56. Okay, iron 56 with binding iron 56 having the binding energy of this. So if we will compare the nucleus stability of iron and the uranium, so we will say uranium have the binding energy this, and iron has the binding energy this. Uranium has the more binding energy, so uranium as compared to the iron will be more stable. But this is not true. This is not true. Stability is not depends upon the binding energy. Stability is depends upon the binding energy per nucleon. Because more will be the mass number, more will be the binding energy, but at the same time, more will be the number of nucleons to manage. Okay. So basically, this is the curve given in the NCERT. From this curve, we will conclude some result. So basically, this is the curve of the binding energy per nucleon versus mass number. So on this axis, this is the binding energy per nucleon in mega electron volt, and this is the mass number. Okay. So 0 mass number 50, 100, 150, 200, 250, and here is the binding energy per nucleon. Now see this graph. First, the binding energy is increasing from hydrogen to helium, then decreasing, then increasing, then decreasing, then decreasing, then increasing, then maximum binding energy is of iron. Now from iron, the binding energy starts decreasing. Okay, you can see from here the binding energy start decreasing. This uranium have binding energy approximately 7 point something, okay, per nucleon. So basically this is the curve. Okay. So no need to learn this curve. There are some results that you have to remember. From mass number 50 to 80, binding energy per nucleon is basically approximately equal to 8.5 mega electron volt. Now we will see from the graph 0 to 50 mass number, from 0 to 50 mass number, you can see the binding energy is basically 8.5, approximately 8.5. Okay, here this is 8, here will be, here somewhere will be 8.5. So 50 to 8, 50 to 80. From not from here to here, from 50 to 80 means this is 50, this is 0, this is 25, this is 50, this is, here will be 75. So somewhere something here, from here to here, 50 to 80, so 80 will be somewhere here approximately. So you can see here the binding energy, average binding energy, when you will calculate, it will be come out to be 8 point something, means 8.5 mega electron volt. So these nucleus are stable nucleus. So the nuclei of element having mass number 50 to 80 are stable nuclei having large binding energy per nucleon. Okay. After that, iron mass number 56. So it is having a binding energy per nucleon 8.8, has the highest binding energy per nucleons, and hence the most stable nucleus. So iron have the most stable nucleus because iron, you can see, iron is on the top. Iron is having the maximum binding energy per nucleon. That is why iron nucleus is the most stable nucleus. Third point, for at mass number greater than 80, the binding energy per nucleon decreases slowly, and for mass number 238, it reaches to 7.6. Now see from mass number greater than 80. So from here, greater than 80 means from here, you can see from here the binding energy, see the binding energy curve. See the binding energy curve. From 80, the binding energy per nucleon is decreasing, and finally this uranium have the binding energy of 7 point something, 7.6 mega electron volt. So basically these are the heavy nucleus. More mass number, more volume means heavy nucleus, you can say. So these heavy nucleus having less binding energy, and these are unstable. So these heavy nucleus are unstable. So if some these are heavy nucleus and these are unstable also. So these nucleus will try to split and try to gain the stability, and these nucleus gain the stability through nuclear fission. We will study that nuclear fission. Okay, after that, for mass number less than 50, mass number less than 50 means from here to here. Okay, see this portion of the graph. Mass number less than 50. You can see the binding energy per nucleon is decreasing sharply here. Is decreasing sharply. So binding energy is decreasing sharply per nucleon. The binding energy, oh, for mass number less than 50, the binding energy per nucleon decreases sharply and reaches to 1.1 mega electron volt for hydrogen 2. Okay, so it will be approximately equal to 1.1 mega electron volt for, it is 1.1 for hydrogen 2. So basically mass number is less, so these nuclei are smaller in size, or you can say these nuclei are lighter nuclei. So these have the less binding energy per nucleon, means these are less stable. So what they will do to gain the stability? They will do nuclear fusion. They will combine with they will combine. Okay, that is known as the nuclear fission and nuclear fusion. Nuclear fission and fusion we will discuss in the next class, and next class will be the last class of your syllabus. Okay, so in the upcoming last class, I will finish this chapter as well as the semiconductor devices. I will try to finish. Okay.
Yes, sir. Okay.
So now, fastly take the screenshot one by one. Okay. So it will take hardly 10 minutes. Okay. So I am zooming.
Yes, sir. Okay.
Done.
Yes, sir. Done.
Okay. So arrange these screenshots in proper manner, and at least once I think you should revise these. Okay.
Yes, sir. Okay.
Okay.
Yes, sir. Done.
Okay.
Yes, sir, done.
Okay.
Yes, sir, done.
Okay.
Done, sir. Yes, sir, done.
Okay.
Yes, sir, done. Yes, sir, done.
Okay.
Yes, sir, done.
Okay.
Done, sir.
Okay. So, next topic.
Done, sir.
Okay.
Done, sir.
Okay.
Yes, sir, done.
Okay. So, next topic. This is the question.
Yes, sir.
Okay.
Yes, sir, done.
Okay.
Yes, sir, done.
Okay.
Yes, sir, done.
Okay.
Done, sir.
Okay.